Hi everybody, Physics Ninja here. Today I want to look at the projectile motion on an incline. What that means is I'm launching this projectile at some angle phi with respect to the ground, except now the ground itself is sloped upward. It's sloped and it makes some angle theta with respect to the horizontal. So I got two questions I want to look at today. I want to first calculate where is it actually going to land on this sloped surface. And the other question is, well, what angle would give you the maximum range? Right? If you wanted to launch it as far as possible, what angle should I make that angle phi in order to get that maximum range? Again, always measured with respect to the incline. Okay, remember the deal. If you like the video, give it a thumbs up. Also, consider subscribing to my channel. We do a lot of cool stuff here. All right, let's get started. Okay, so to set this up, what we're going to do is just use our standard coordinate system here. I'm going to call the x direction this one. Call the y this one. Remember, the acceleration due to gravity is always straight down at every single point in its motion. And, well, again, we're going to have some initial velocity here, v0. That's directed at some angle phi with respect to the surface of the ramp. And the ramp makes an angle theta. So automatically, should be able to write that the initial velocity in the x and the initial velocity in the y direction, these ones you should be able to write down right away. This is simply v0. And this will be cos. Now be a little bit careful here. It's both angles here, because this is my coordinate system. So I really have to break things down into x and y coordinate systems. Here you have sine of the same angle, phi plus theta. All right. Next thing you can do now is you can analyze the motion along the x direction. This is exactly the same as just the regular projectile, right? So along the x direction, what do you get? Along the x direction, if you're just looking for the position, and imagine here I'm just starting at the origin, so there's no initial position, just set that to 0. What you're simply looking at here is the initial velocity in the x direction multiplied by time. That's it. There's no acceleration over here. How about in the y direction? In the y direction, well, again, pretty straightforward. The y position, the vertical position, is my initial velocity in the y direction multiplied by time. And again, then it's minus 1/2 little g times t squared. Same equations you have for regular projectile motion. So how do you actually introduce the ramp over here? Well, if you think about it, what is this vertical direction here? This vertical direction, we're going to call this y. And the horizontal one is x. Let me make that in a different color here so we can see this is the horizontal distance. This is what we call x. And the way you link them now, well, if you think about it, I know the angle theta. That's true for every y and x value. Actually, you can see that tangent of the angle theta is simply equal to y over x. Actually, if you rearrange this a little bit, I just change the color here, you're going to find that the height, the vertical height, is simply equal, just bring x on the other side here, you get tangent of the angle theta multiplied by x. So this here is our equation that tells us where the surface of the ramp is for every value of x. Okay, so the next thing we're going to do now, we're going to link this back to our projectile positions in just a minute, but let's just first substitute what the initial components of the velocity are in the x and y equations. So for the x direction, what do we get? v0 cos of our angle phi plus theta multiplied by t. And in the y direction, we get v0 sine of the angle phi plus theta multiplied by t. Again, minus 1/2 gt squared. Okay, now in order just to have one expression here, I'm actually going to eliminate time in this second equation. And I'm going to eliminate time by using the information I have for the x component. So for that, I can automatically see that the time from my x equation here is simply x divided by v0 cos of phi plus theta. You have an expression for time. We could substitute this now into the equation for the vertical position of my projectile, and then just have something, a function of y versus x. I mean, there's some complicated trigonometric functions in there, but that's not really a big concern for us. Okay, so let's do that. So the last step over here is y is equal to, So now instead of writing time, I'm going to substitute time with everything here. You see the v naughts cancel here for this first term. The second term, I'm going to have sine of this term divided by cos. Let's just group that right away as the tangent, just to simplify the expression as much as we can. And now you're still going to have an x here. And minus 1/2. There's not much you can do for the second term. T squared, let's just open up a big bracket here and just substitute everything in here. This is going to be x squared. This is going to be v naught squared. And this here is going to be cos squared of this whole thing, of phi plus theta. Okay. So actually, I haven't really done a whole bunch. Now we have this kind of important relationship. And basically what we want to do now is we want to solve this equation. However, we want to solve it for which value of y do we want? Well, we want it to land on the ramp. So we actually want to solve this when the value of y right here is equal to the vertical position of the ramp. Right? For any value of x, we know what the vertical position of the ramp is. So this is actually what you want to end up doing here. So let me go ahead and kind of just remove this guy for a second and replace it by tangent of theta multiplied by x, because this is the equation we want to end up solving. So instead of writing y, as I just did, let's go ahead and substitute it with this. So this will be tangent of theta multiplied by x. Now this looks like a nasty equation, but it simplifies pretty nicely. You can already see one of the solutions, right? We automatically have that x equals to 0 is a solution to this equation. Right? Substitute x equals to 0 here, you get 0 here, you get 0 here, and you get 0 here. That's one of the solutions. X equals to 0 is a solution. And that's just because that's the launch point, right? That's when the ball is directly on the surface here, right at the launch point. Actually, what we want is we want the other one, right? After it kind of goes up for a while and then comes back down. This is the other solution that we're looking for. So there's actually two solutions to this equation because it's a quadratic equation. So let's go ahead on the other page now and solve what the other solution to this equation is. Okay, so this is where we left off. We've got our equation for the ramp. And remember now, everything on this side is really the ramp. This is the vertical position of the ramp. And what we want that to be equal to the vertical position of the projectile. And when they're the same, well, they're going to be at the same position. So the next thing we want to do now, just solve this equation here for x. So I'm going to bring this term on the other side and group some of the terms and just clean this expression up a little bit. So we're going to have 0, let's just make some room, 0 equal to, here I'm going to have tangent. Let's look at all the terms that are linear in x plus phi minus tangent of theta. All of this gets multiplied by x. And now minus 1/2 g over v naught squared x squared divided by this whole bit, cos squared of theta plus phi. Okay, so automatically you could see that if you cross out one of the x's, because we already have the x equals to 0 solution, so let's get rid of this one, and let's get rid of this one. And now you simply solve this equation for x. So I can bring everything on this side, and what am I left with? X divided by cos squared phi plus theta. Let's not forget those constant terms here. I have the 1/2 little g v naught squared. And this here has to be equal to this trigonometric function over here of phi plus theta minus tangent of theta. All right, and the last step now, just isolate x. If you isolate x, you end up getting 2 v0 squared divided by g. This whole trigonometric function again, tangent of phi plus theta minus tangent of theta. Now, it looks really messy, but it's just math. Don't worry about it. Divided by, actually in this case it's not divided by, because if I bring this cos squared term on the other side, let's get rid of that. You're just going to get cos squared of phi plus theta. Now that's the x value. That's what this value is. That's not really along the incline, is it? Along the incline would be how far is this distance over here, right? This is really what we're asking for. And this is what you call the range typically. And the range you can automatically write, well, if you have this expression over here, you know that x should be equal to the range multiplied by cos of theta. And that's what we just found. But really what we want here is this value r. That's the range measured along the incline. So from this expression, you can see right away that r is going to be x divided by cos theta. So really, if we want to know the value r right here, we need to take our value of x and we need to divide it by cos of theta. Okay, so what I'm going to do here is I'm also going to divide by cos of theta. And now this is what we're looking for. All right, now this is our expression. Wow, it looks pretty messy. A lot of different terms in there, but this gives you a value of the range for this guy. That automatically tells you, well, again, these are given by the problem, right? This is just one big trigonometric function, something you plug into your calculator given whatever slope you have. And I'm the one who decides where I want to launch my projectile. So, given some information of a problem, I'd be able to find how far the range is as measured along this ramp. All right, so that's kind of part A. And part B now I want to see for which angle of this angle phi would the range be maximum. Okay, so how do we actually maximize this function? And for that, we're going to use some trigonometric identities, but it's pretty straightforward. So let's go on the next page and I'll show you how to do that. All right, so here's the expression for the range, and our goal now is to maximize this trigonometric function, right? The front here, both of the, these terms over here are just a constant value, so there's nothing you can change there. However, for which value of phi would you maximize this complicated function? So in order to do that, what I'm going to do is I'm going to introduce a different variable over here. Let's call the angle alpha, just to simplify all these terms, phi plus theta. Okay, so you're just going to make a change of variable just to clean things up. All right, so we're going to have 2v0 squared divided by little g. That's our constant term. And now we have all of this, which I can clean up a little bit. So we have tangent of alpha this time, minus tangent of theta, and cos squared of alpha over cos of theta. All right, that's pretty straightforward. The next thing now, I'm going to expand some of these terms. So let's go over here. The range is going to be equal to 2v0 squared divided by little g. Again, we're going to have to use some trickery here. So this is going to be sine of alpha over cos, right? Minus, again, sine of theta over cos. And all of this gets multiplied by cos squared of alpha, cos of theta. All right, you can multiply through. Okay. If you multiply through, again, the constant term, nothing changes with that one. All right, now we're going to be a little bit careful here. So we have sine of alpha and cos squared of alpha. However, there's a cos down here, so that's going to cancel out. So you're going to be left with sine of alpha. Nothing can happen to that term. You're going to be left with cos of alpha divided by cos of theta. That's what happens when you multiply this term here by the first one. And the second term now becomes minus sine of theta cos squared of alpha. And this gets divided by cos squared of theta. All right, that was just pretty straightforward. And next thing, let me simplify this a little bit more. Again, it's always the range. I'm going to factor out this term in the denominator, and I'm also going to factor it out from here. Maybe I shouldn't have multiplied it through, but all right, and here I'm going to have 1 over cos squared of theta. You'll see why I do this in just a minute. All right, so now you got to be a bit careful here. So that means this term here becomes sine of alpha, cos of alpha, cos of theta, and this term just becomes sine of theta, cos squared of alpha. All right, so you notice here I have an extra cos of theta because I did factor the squared term out. Okay, now we're going to use two trigonometric identities in order to simplify this. It's almost a very similar approach to what you do if you're just looking at regular projectiles. So the two identities that I'm going to use are these: sine of alpha, cos of alpha. You can use some of these double angle equations. This is sine of 2 alpha. And number 2 is cos squared. You can write that as 1/2 and 1 plus cos of 2 alpha. So I can eliminate this guy, and I can also simplify this. Okay. The term in the front, look at it. The term in the front doesn't depend on the angle phi. It only depends on properties of the ramp. So actually this term really has nothing to do with maximizing the range. So anyway, we could just continue this. Now if we substitute everything in here, this is what you end up getting. So we're going to get 2v0 squared divided by little g. Let's just write those down. 1 over cos squared of theta. Okay, now comes where you have to be a little bit careful. So sine of alpha multiplied by cos alpha, I replace it by this, 1/2. Sine of 2 alpha. That is still multiplied by cos of the angle theta. Okay. Minus sine of theta. Now cos squared of alpha over here, again, I'm going to use this double angle formula. So you're going to get 1/2 and 1 plus cos of 2 alpha. All right, we're going to do one more step here. Really, I'm just going to simplify what's in this square bracket. Well, let's just rewrite it all. I should have maybe just called all this some other variable, but okay. That's fine. Now let's be a little bit careful with these three terms. Actually, I could factor out a 1/2. Let's do that. So you see if I factor out a 1/2, it's going to cancel with that 2. So let's do that. So all of these 1/2s here are basically going to cancel with this 2. So let's get rid of that 2. All right, so here you're simply left with, okay, sine of 2 alpha cos of theta. What else? You have minus sine of theta. Let me just write this other one, cos of 2 alpha. And then at the end, you're still left with minus sine of theta. All right. Now, this over here. This here can be simplified. Let's scroll down a little bit. Give me a little bit of extra space. You can always go back in the video and double check stuff after. All right, so we're almost done here. Actually, here you can rewrite this term. All right, this here is nothing more than sine of the angle of 2 alpha minus theta. All right, those are, again, using just one of the trigonometric identities. All right, on our last step now, we just group everything together. So let's rewrite this final expression. And there's probably more elegant ways of doing this. Again, I'm just showing you one way that I know works. The math is tedious, but it is still straightforward. There's no gimmicks here. And the only reason I'm doing all of these substitutions is at the end, I just want to look at the expressions. I'm sure if you differentiate that with respect to our angle, set that to 0, you could probably do about a week's worth of algebra and eventually get to the same answer. But this is how I'm going to do it. Okay, so now let's go back and get rid of so this is kind of a nice simple expression. Let's go back and eliminate what our angle alpha was. If you remember, alpha was simply theta plus phi. So we simply get okay, so here we get 2. This is theta plus phi. Now careful, it's right, both of those get multiplied by this double angle here. Minus theta and minus sine of the angle theta. Okay. You get 2 theta minus theta. This is the last expression I write, I promise. Then we'll look at some limiting cases to make sure that our complicated expression kind of looks good. All right, so this becomes sine of 2 times the angle phi minus the angle theta, and I should say plus the angle theta, and minus sine of theta. All right, there's my expression for the range. It's the exact same expression as what you previously had. However, it's just in a nice compact form. Right? Kind of nice having these double angle formulas. We've rewritten our range equation to look like in this compact form. Whenever you do a whole bunch of algebra like this, it's always a good idea to take some limits to make sure whatever you did doesn't make sense. So if it doesn't, you've done a mistake somewhere. So case one. Case one, what happens if the angle theta equals to 0? Well, if theta is there, that automatically means that there is no incline. And the surface is simply a horizontal surface. And in that case, we know the result. So let's make sure that our equation works for that case. What would be the range for that case? Well, v0 squared divided by little g, that's the same. 1 divided by cos of 0. Cos of 0 is 1. You don't have to worry about that term. What else are we left with? We're going to be left with sine of 2 times phi plus 0. I don't have to worry about that. Minus sine of 0. That's also 0. Actually, this is the expression that you get for the range. And you can look this up in textbooks. And what you find is that you would maximize the range for this case. If there is no incline, you'd maximize the range if the angle phi was equal to what? Well, what you want is you want sine of whatever the angle is to be 90, right? So phi would have to be 45 degrees in this case. That would maximize this angular term, and then you'd get the maximum range for that case. All right, what about the more general case now? So the general case, the argument is the same, is that the term in here, you really want this to be equal to 90 degrees. Because sine of 90 degrees equals to 1. That's how the biggest you can get. So for the general case, really what we're looking for here is that we want 2 times the angle phi plus theta to be equal to 90 degrees. So that means that our angle phi should be equal to, again, bring theta on the other side, divide through by 2. So that gives you 45 minus theta divided by 2. Okay. So this here is really what the maximum angle should be to give us the range, to give us the maximum range. Let's box that and let's look at a couple other cases. Okay. So let's take the case maybe when, what happens if the angle theta is actually minus 90 degrees? What does that look like? It would look like this. Remember, here's 0 degrees. Here's the ball. So what would minus 90 degrees look like? Well, it would look like down here, right? This would be a vertical wall. In the case of a vertical wall, what would our angle phi equal to if I want to maximize the range? So in this case here, what you would end up getting is that you would want phi to be equal to 45 degrees minus 90 over 2. That gives you what? This here will give me minus 45 degrees. You get 45 plus 45 degrees, and that gives me 90 degrees. Now, what is 90 degrees? Well, again, that angle phi, remember, is always measured with respect to the surface. So the 90 degrees would tell me that, well, 90 degrees measured with respect to the surface, with respect to the vertical wall, is this. That's 90 degrees. That would be the angle phi, which would mean that I'm launching this projectile horizontally here at some initial velocity v0. That's how I would maximize the range, because the projectile would simply go like this, and I'd be at some distance r away from that vertical wall. All right, maybe one more case. Case 3. This one's not really a limited case that I think you would kind of know, but what if the angle, for example, was 30 degrees? Right? A 30-degree incline, well, the angle phi that would maximize the range for any initial velocity would be 45 minus 30 over 2, so that's 15. Actually, it would also give me 30 degrees, which is kind of interesting. Okay. Then you can go ahead and substitute that and actually calculate what value of the range you would get. But again, it depends on the initial velocity that you launch it. Okay. Anyway, that's how you set up the problem, folks. Again, a little bit tedious on the math this time, only because I really wanted to get to a nice friendly expression for the range. If I was happy with the first expression, it just didn't lend itself very well to finding what the maximum value was, which is why I kind of wanted to follow up with it and do it and write it in a simpler form. All right, that's it for me, folks. Thanks for watching.